goes again. So the last talk in this session is given by Johannes Klepsch, and it's about, well, sort of a perspective of where quantum computing might be actually applied in industry. So the talk is given by a representative of BMW, which is of course a very important presence in Munich for us. And so yeah, he's going to tell us where BMW is hoping to take advantage of quantum computing. You're all a go.
Excellent. Yes, thank you very much. I'm Johannes from BMW Group IT. And yeah, let me start by saying how honored we are to be one of the sponsors of this event, and especially to be allowed to share kind of our perspective on quantum computing, right? And let me also echo what the previous speaker said in terms of thanking the organizers for setting this up. Yeah, I can only imagine how hard and complex it must have been, especially with the size of the whole thing. So excellent job, and thank you very much. So today what I want to do is to talk about two things, right? On the one side, I want to give you guys an idea as to the complexity of the automotive value chain, and hopefully convince you that automotive is a promising candidate for the application of quantum technologies. And then on the other side, I want to give you some insights as to why and what BMW does in this domain, and like what our journey kind of looks like. And yeah, as mentioned, right, we're more on the applied side of things compared to what was discussed before. So I think we are able to bring kind of a different perspective onto the whole onto the topic. Right. So let me start by giving you a brief introduction into the BMW Group IT. We are more than 4,500 employees that are really located all around the globe. We work in 29 different countries. And why am I telling you that? It's because, well, it's kind of important to understand how QC started within BMW, right? So the way we operate is that we have tech offices all around the world who are able to kind of, move a little bit more quickly, I would say, than we do here in the headquarters. They're able to interact with the local markets, and this is really where 4 to 5 years ago we had our first touch points with quantum computing, mainly in the States, obviously, and in Singapore. And let me give you an idea as to how the topic kind of developed since then, right? So as mentioned, we started in like 2017, where quantum computing appeared on our corporate technology trend radars. And back then it was identified as a potential game changer technology, right? And since then, it kind of went the normal process. We carried out first proof of concepts. We formed a network. We wrote some technology reports, to get higher management on board. And in 2020, this is when, well, I would say the development really shifted gears, as quantum computing is really now one of the Group IT's strategic initiatives, and we're really able to accelerate our journey and our know-how build-up, and really engage in a more kind of long-term manner. And yeah, I think this is a good point also to emphasize that even though we do look at applications, right, we're really very well aware of the long-term nature of our investments into quantum computing. And our approach is really a collaborative approach, right? We really do understand that in order to understand the technology, you have to do research, right? And we're really willing to engage also in foundational research in the field. So this slide is supposed to kind of showcase that we do have opportunities along our entire value chain, right? So what you see here on the left is basically the automotive value chain that goes from research and development all the way to manufacturing, and then even support and administration. And we really do see potentials along the entire value chain, and let me maybe dive a little bit deeper on what these are potentially, right? And I won't go through all of them, but I've picked a few topics that I'm sure are not unfamiliar to most of you, but nevertheless, I think you all know as well that many components these days are designed and tested or I should maybe say pre-tested using computer simulation, not quantum simulation. Well, due to the limitations computing power, what you normally do is you take like individual components, right? You kind of simulate them, and in order, or since you can't really model the entire integrated system, what you have to do is to kind of take certain safety precautions, add some margins to your simulations, just to be on the safe side. And when you aggregate those margins, well, you're not really sure whether you really reach the optimal kind of model that you want to work with, right? And the promise that we see, or that quantum computing might bring to the game in terms of like numerical simulations, is really to be able to model integrated systems and including the interactions between these subcomponents, which we hope could then reduce the cumulative impact of these safety margins. One other topic that I can briefly mention, I think it's been communicated so many times already by probably almost every car manufacturer out there, but nevertheless, I think the electrification domain is obviously like one of the most kind of strategic pillars of car manufacturers today. And I mean, battery simulation is a big deal, right? And battery development is particularly. And we also hope that quantum computing or at least it promises to push the boundaries of what could be technically feasible in chemistry simulation, to accurately simulate the behavior of molecules. And so this is definitely another part that is very interesting. And then for the rest of the topics that are on the slide here, a key topic is, of course, optimization, and this is what I will focus on in the remainder of today's talk. Good. So bit of background into automotive. So the design of a vehicle is a super complex process, right? It involves many different disciplines, from manufacturing to distribution. You have hardware engineering in there, software engineering, electrical engineering. And additionally, what you have is very high standards when it comes to like performance metrics, right? Think about durability, think about safety, think about aerodynamics, think about costs as well. And what we've seen over the last decades, it's only getting more complex and more complicated, right? There are three main developments that I want to point out. So on the one side, we have increasing electronic software and service content. Right, so our software stack in vehicles is reaching hundreds of millions of lines of code. We additionally, as a second trend, observe a strong trend towards connected and automated mobility, right? And which obviously integrates a whole new kind of dimension of complexity. And then, as a third trend, in pretty much every industry, we do see a strong trend towards globalization, right? Our plants and our suppliers are located all over the world. We're now producing in 31 different plants, and we have more than 100 different models that we produce, right? And all of that added complexity over the years obviously has to be managed. And in order to be able to do so, well, you have to plan, right? What we try to do is to kind of structure in different kind of layers of planning. And we do think that this alignment between these different layers is crucial to improve quality on the one side, but obviously it adds complexity as well, right? Now, what I will do next is to kind of guide you through these different layers of planning. And whilst doing that, I want to give you an idea as to some examples of optimization problems that arise. So let me start at the very top, right? Use cases in strategic corporate planning. So I think everybody is well aware of the fact that digitization these days has kind of increased availability of data. And especially in automotive, this is the case, right? We've reached the point where we are aggregating data in our own company and are now going towards partners, try to get this integrated view of data along our entire supply chain as well. And we hope that in the long run, this data will provide us with the ability to really support long-term strategic decision making, right? And what do I mean by that? Think about, for example, a problem like, you know, you want to build a new plant. Where do you want to build it, right? So you have a very, very complex constraints such as capacities, logistics, right? Like what suppliers are located in that market. You have airports, you have, you know, trains, whatever. Labor costs obviously plays a great role, and recently the topic of customs has been getting more important as well. Then as soon as you've decided on where you want to build your plant, you have to allocate vehicle models to these plants, right? So I don't know, do you want to build your new X3 in China or the States, right? What are the constraints that you take into account there? Like normally you'd probably want to, you know, build the model where it's bought, but does that fit to the constraints these days? And then another important decision is your product mix, right? Like these days, obviously everything is going towards electrification. Like what's your percentage of electrified vehicles that you want to produce and sell? And the mother of our questions is always of course the sales volume, right? So how many cars do you want to build in the very end? If you kind of go one step further down the line in our planning layer, you have to understand how you know automotive production works, right? So we basically think in terms of production lines, right? So the car body, which is in the very beginning just, you know, a white body, and kind of traverses the production line continuously. And as it goes along, you know, additional components are added and are integrated along the way, and basically have different workstations, and each of them has to perform their task in a given cycle time, right, in order for the line to keep running. And yeah, so the first problem really is to optimize the line, right? So this is something that we call line balancing. So what you want to do is to assign the different tasks that you have to the workstations, and you have basically two main goals, right? The first one, given that you have a fixed cycle time, right? So for example, in Munich, in the plant here, we have a cycle time of around about, I think, a minute. So basically every minute a car leaves the factory. And the question is like, you want to minimize the workstations that you have for a fixed cycle time. Now go one step further, say you've minimized the cycle time. What you can then do is to try to, you know, or sorry, now say you fix the number of workstations, and now you want to minimize the cycle time, right? And basically optimally you do both things at the same time, like minimizing the cycle time whilst minimizing the number of workstations that are needed. Another problem that occurs in line balancing is to optimize buffer capacities, right? So you have to kind of get some resilience going in your supply or in your working production lines to be, you know, operational in case of interruptions of the line. And yeah, so there are a lot of optimization issues to be solved. And then another topic that we do see, vehicle scheduling, right? So assume, okay, your line is balanced, right? You've set up your workstations, you've set up your cycle time. How do you schedule the vehicles that will then be produced, right? So what you have to understand is that depending on the vehicle type and the model and the configuration, there are strong differences as to the complexity of building it, right? So imagine a plug-in hybrid is probably going to be much more complicated to build than a standard diesel vehicle. So you have to make sure that you know, you schedule the vehicles accordingly so that, you know, lines don't kind of fall behind, or workstations don't fall behind. So you want to kind of, you know, distribute them in such a way that complex vehicles are followed by less complex vehicles. And last but not least, you have shift scheduling, right? So many of the steps along the production lines are handled by robots these days, but especially in assembly, you do need specialized workflows to take care of the assembly. And therefore you have to, you know, schedule shifts accordingly, which is a surprisingly complex task, especially because you have a very complex boundary conditions, like you know, resting periods, holidays. You have allocation of night to day shifts, etc. So there is again a lot of room for optimization. Now, let's go one step further in the production or in the planning processes, right? And now we've reached basically use cases in manufacturing planning, and we've depicted here a couple of applications that we do see in the domain of robot path planning. So as mentioned, a lot of the production steps are handled by robots, right? And basically, wherever you have a robot that is, traversing a set of nodes to do their jobs, you have the potential of optimizing the path that it is taking, right? And yeah, so we have a couple of use cases depicted here, like painting, gluing, sealing. And what I will do now is to give you guys a small deep dive into the use case of PVC sealing, as it's been one of the cases that we've been working on for quite some years now. And the reason why I want to do that is not because we're going to, because we have come up with a lot of novel technologies, but rather to kind of demonstrate the process that we normally take when it comes to applications, and so we'll try to generalize it after that. So let me start by introducing the use case. So in automobile production, you have PVC, which is some plastic that is applied to the body, and it is applied wherever you have basically different metal sheets that come together. So these metal sheets then form seams, and these seams have to be sealed. And in many cases, the work is carried out by robots, and these are programmed to follow a specific path along the vehicle body. And the challenge now, obviously, is to find a collision-free path such that the task can be completed in a minimum time. Simple enough. Now, as you've seen, there are multiple robots basically on one workstation, right? So you have basically two different tasks here. On the one side, you have to do a scheduling, right? So what robot takes care of what seams? And the second problem then is sequencing. So you want to basically minimize the routes for all robots and create a collision-free path. Now, this looks like the standard traveling salesman problem at first, but there are a couple of differences. First, you're not required to visit every node in the underlying graph, right? You only want to visit nodes that are connected by a seam. So many nodes are actually left untouched. And then you have another difference because certain nodes must be connected, right? So you're not free to just simply move around the graph and connect arbitrary vertices, but yeah, you really want to only connect the ones where you have a seam in between. Good. So why is this problem so complex? Basically, you can imagine that per workstation, you have 3 to 6 nozzles that cover overlapping areas of the underbody. Per robot, you have different nozzles depending on the type of PVC that needs to be applied. And then per region that is reached by one robot, you have like up to 80 different seams that have to be sealed. And that's for like from one car, you have about 200 seams that have to be sealed. And on top, different car models need different, have different seams that you have to take care of. So basically, you need a different plan for every robot and even for different configurations of the same vehicle type. So in the end, you have a huge solution space that you can target. And what we do today, because as you saw, the robots are already doing their job, we solve these problems heuristically, we use nearest neighbor approaches, and we do all right, but we can show that basically the lower bound of what can be achieved is actually much lower than what we do. Okay, so let us go through the process of what we did with that use case. We started by formulating it as a QIP problem, knowing that this is not the optimal formalization of the problem. But basically what we did, let me guide you through the steps here real quick, is to basically assign binary variables to the decision of whether we assign, say, seam I. I'm not sure whether you can see my pointer here, seam I to the robot at time step t in the direction k, right? Because you can either traverse a seam in one way or the other. Then basically every seam or every edge of the graph is associated with a weight. And in the simplest case, we could just take the distance here, even though this is a simplification because, you know, robots might be quicker on you know, this distance than on another one, depending on where it's located in the underbody. And then we formulate our cost function just the distance traveled between the different points. We have to add some constraints, right? We need to make sure that each seam is sealed exactly once. And we also have to make sure that the robot only seals one seam at a time. And yeah, then we add those constraints to our cost function using some constant. And yeah, that then leads to a cost function that potentially can be solved on quantum or quantum inspired hardware. Yeah, let me visualize the results. I'm not sure whether you can see the video here. Let me try to start it. So basically we start by sampling the robot workspace with nodes, right? In order to be able to know, okay, what are the different routes that a robot can take from one point on the car body to another. We then compute the weight matrix. We optimize the cost function, as you can see here, actually, in order to make sure that the robots do not collide. We draw some boundary boxes around them. Yeah, and then we run that problem on all sorts of different hardware. And this slide is really to be taken with a grain of salt. It's a highly qualitative representation. A lot of assumptions have to be made in order to come up with the studies that we hear. But generally, what we try to do is to compare the solution quality and the problem sizes of different hardware setups, and with the problem that we were running, and at the same time, kind of predict the viability of our solution with respect to the hardware roadmaps that were offered. And yeah, we observed that there are some pretty strong limitations as to the viability of the different hardware setups due to the general challenge that arises not only in terms of the scalability of the hardware, but mostly also because of the restrictions in terms of the formulation as a QIP problem, right? And obviously, without going into too many details, if you take further assumptions on possible improvements on hardware, right, you come up with better prediction in terms of solution quality. But that's not the point of today's talk. What I really want to spend my last minute on, and this is really an important point, so bear with me, is to illustrate the general approach that we're taking here, right? So what we do is that we basically have these two ways of approaching problems. On the one side, we investigate available quantum solutions. We focus on hardware, existing quantum algorithms, and on the other side, we have high-level applications that we try to derive from real-world industry applications, right? And both approaches optimally complement each other, right? We have progress on low-level challenges that can inspire new industrial applications, and high-impact industrial problems can accelerate progress on algorithms, right? Due to the commercial relevance, basically. Now, the third pillar, and this is actually the most important one for us these days, is standardized benchmarks, right? We need to be able to compare systems designs to guide progress. And what we see is that currently benchmarks often only focus on low-level aspects, such as like gate validity, but we see a lack of application and end-to-end benchmarks, right? And we do really need those to push development forward towards real-world problems. And so this is really what we do. We try to define reference problems, right, as an enabler for these benchmark suites. We formulate also based on this approach requirements towards our partners that we try to engage with, both in academia and applied research. And we try to formulate these industrialization roadmaps and maybe improve the quality of the roadmaps that we just depicted a couple of slides back. But this is really what we're striving with in order to prepare our business to be basically quantum ready whenever it hits in the next decades. And with that, yeah, I think I'm running out of time. So just real quick, our step forward, right? As mentioned, we really want to focus on research collaboration. We're committed to long-term research engagement. We want to focus on these reference problems for the creation of industry benchmark suites. We do look for strategic partnerships, right? We think this collaborative approach is the way forward. Alliances between startups, researchers, you know, in our case, car manufacturers. And last but not least, we welcome the MCQST approach of open communities. We do want to foster this open source mentality. It's funny, co-creation fits beautifully to what was said before by the colleagues from IQM. And we do want to engage actively with the community. With that, thank you very much. We also are hiring, so please get in touch. And yeah, sorry for being a little bit over time.
Thank you very much for this very nice overview. So yeah, let's give a round of applause. I have a couple of questions actually from the chat. So Andras Chegel asks, I mean, if I may paraphrase, I mean, you have your optimization problems. Do you think that do you see your work or the potential more in kind of adapting these problems and their formulation to the quantum computing architectures that exist, or do you think it's more helpful to try to build quantum computing devices directly suitable for the combinatorial, for the optimization problems?
Well, I think we're applicants of the technology that we do have at our hands, right? And our strength is obviously not on building quantum computers, and actually to this point also not yet on building quantum computing algorithms, right? Our strength as a company first and foremost is in, you know, domain knowledge, right? Like we understand the business of building cars, and so basically we have to take that as a basis and then build from there, right? And then as a next step, you know, oftentimes we do start from that, you know, top-down approach of having these high-level industry applications, and then kind of go from there. And whilst doing it, build up the know-how in order to be really able to compile these benchmarks that I was talking about on all the different levels of the stacks, right? So at least be able to comprehend what is going on the lower levels as well. And yeah, maybe basically for the POC that I've showed, right? Like, what do we learn? Obviously, we didn't well have any advantage in terms of running the algorithms on quantum hardware. But what came out of it is, well, we understood, we learned a lot, right? We are able now to kind of understand a little bit more as to what algorithms will be ready. But first and foremost, we really got to understand the underlying optimization problems in a very concrete and concise way, and might actually be able to, you know, use that knowledge to solve them in a more efficient way that might not always be only on quantum computers, but that domain knowledge is an important factor for us for sure. Thank you for the question.
Yeah, I mean, that is kind of from a theory side, it was obvious that, I mean, clearly you can play a lot with how you translate your real world problem into this minimization problem. I have a couple of more questions. I mean, maybe we can go through them quickly. Seva Caribbean, thanks for the talk. And he asked something exactly that I also wondered. It seems you're really focusing on optimization problems. How does the battery research that you mentioned go into this? Or are you planning to? Are you looking into using quantum computing also for that? Because you mentioned, for example, quantum chemistry. And also, could you comment on this on the QAOL timeline that stretched into like 2028?
Yeah, I was sure that like as soon as you show timelines, right, that always raises questions, and it's yeah, it probably wasn't a good idea to implement it, but this is really what we're targeting in the long run, right? To be able to do these predictions, even though we're not really able to do them right now. So they have to be taken with a grain of salt. And like optimally, if we have like error corrected qubit at some point, we would want to move away from QA and rather focus on other type of algorithms. But maybe we can take that offline. The other question that was asked, I think, in terms of the chemistry use case, right? So today's talk was definitely focused on optimization problems, because I think these are like the most natural kind of problems that you might think of at first, right, when you think quantum in an automotive context. But yeah, maybe the quantum chemistry, material science kind of use cases are the more relevant ones actually, and we do actually also look into them more closely, even though this wasn't the topic in today's talk.
Thank you very much. I mean, okay, maybe we can take the time for the last question. I mean, obviously, you're still in the phase of trying out and things. But how? I mean, Alisa Williams asks, how are you eventually aiming to bring the quantum computing back into the company? So, kind of, for example, for these production lines, are you thinking of outsourcing that, or is that something you wanna
Yeah, that's an excellent question. And we actually, you know, I've been working in the field of emerging technologies for quite some time, right? My background is not necessarily in quantum computing. So this is not a quantum computing specific problem, right? This is really a general problem that has to do with, you know, how do you bring in innovation into the company? And this is like such a big topic. I could talk about that for a very long time. But you're right? Like, I think the first step is really to be able to understand what kind of benefits you can really gain from a technology. And then the next step, and this is often the much longer and harder journey, is to really integrate these innovative topics in existing and productive work streams and work lines, right? And this is really also where we as a team, we see our core competency though, right, is to kind of bridge that transition phase and to make sure that this industrialization of features is really being made. Like, fortunately, we're not quite there yet in terms of quantum computing, but this is what the heavy lifting really is in terms of industry applications, right? To go for that industrialization and that integration of emerging technologies and existing work streams. Great question.
Thanks. Well, I guess that were the questions from the stream. I mean, there might be some other things coming later, but of course there is right now the roundtable. So yeah, thanks again to Johannes, also to the other speakers, Runyao and Bruno.